Hello, everybody. Welcome to another lecture here in physical science. My name is Sir Josh, and our topic this MELC number 7 is about reaction rates. Our main objective for this lecture is to use the simple collision theory to explain the effects of concentration, temperature, and particle size on the rate of reaction. Now, probably you have seen a banana ripening, and you have also seen the chains of your bicycle becoming rusted. And I'm pretty much sure you've also seen a piece of paper turning into ashes. In elementary and in the junior high school, we call these processes as evidence or pieces of evidence of what we call chemical changes. And we will use these examples to describe what we call the rate of reaction, and we will use the collision theory to explain further the rate of reaction of our banana becoming into a ripe one, our iron being rusted, and a piece of paper turning into ash. We define chemical reaction as a process which the atoms of one substance or more substances are being rearranged to form different substances. So in other words, you have this set of substances and then you combine them and then you form a new substance. That is our simple definition of a chemical reaction. Every day there are chemical reactions that we observe or we do. No, you have your combustion, rusting of iron, digestion. That is an example of a chemical reaction. Photosynthesis of our plants, batteries, fermentation, washing of hands, and even baking. These chemical changes are basically caused by chemical reactions, no? Like the ripening of your fruit, your combustion, your fermentation, your photosynthesis. All of these chemical changes are caused by chemical reactions. Just to freshen up and review your previous knowledge on chemical reaction as discussed in your junior high school science, chemical reaction involves two sets of, say, substances. You have the reactants and you have the products. The reactants are the ones that you combine or you mix together, or you need to have them reacted to form new products. So this is a chemical reaction of photosynthesis where you need carbon dioxide and water, and of course sunlight to produce oxygen, and of course your sugar or the glucose. So here from carbon dioxide, water, and sunlight, you're able to form new products. So basically these are the two sets of substances or two components in chemical reaction. Um, in describing chemical reaction, we describe it in a way either we say the chemical reaction is slow or the chemical reaction is fast. Like for example, your iron rusting, this is a slow chemical reaction because this takes time, while a burning wood will consider it as a fast reaction. So we describe them with respect or in terms of their reaction rates. No, either they are slow or fast. But what makes the rate of reaction fast or slow? And I think this is what collision theory is about, no? Describing the rate of reaction at what causes them to be slow or fast. Now, there are three conditions for a reaction to happen. And number one, there must be a collision between particles. Number two, there must be enough or sufficient activation energy. And number three, the collision must be in a correct orientation or at the correct angle of collision. Let us discuss first the activation energy. So as mentioned here, for you to have a chemical reaction, there must be sufficient activation energy. This is our graph. The y-axis represents the energy levels, and the x-axis represents the reaction component. So basically here, for your reactants to become products, let me grab my pointy here. For your reactants to become new substances or for you to form products, you must be able to um, reach this certain energy level, which we call the activation energy, for you to achieve the transition state. So just to give you a visualization of this, like if you have a certain piece of paper, if you wish to convert your piece of paper into ashes, there is a required activation energy, there's a required temperature, there's a required heat, no, for your paper to become ashes. So the same thing with the general depiction of the need for the sufficient activation energy. There's a certain requirement for the transition state to happen, meaning the change or the formation of new products to happen. I have here a simulation using the FET simulation by University of Colorado. Basically here, you have a graph representing the energy and the reaction coordinate. So let us try to give just a small amount of energy. So you can see here, this green bar here, or the green line, represents the level of energy that you provide or you will give to your reaction. So let's say we'll just give a minimal energy below the activation energy. No? So we will give some energy, and all right, just below the activation energy needed. So as you can see, all right, this line here, which is I think grayish line, is not moving. It's moving, but it is not moving beyond the transition point, which is here. So the collision here is happening, but look, observe the gray line. It's not moving forward after the transition state, meaning to say the activation energy that we provided here, or the energy that we provided here, was not sufficient for a reaction to happen. Now let us try to reset it and try to observe what happens if we provide an energy that is sufficient and above, no, or more than the required activation energy. Let's take a look what happens and observe the gray line there, the gray vertical line, if it passes the transition state point. So there is a collision, and as you can see, the white line here, whitish or grayish line, vertical line, passes through the transition state, meaning to say your energy was sufficient enough to produce a chemical reaction and thus a new substance. So basically, that is what is meant by your graph here, that you need sufficient activation energy for you to achieve the transition state and therefore come up with new products. So the same example with um, the piece of paper converting into ashes, it requires certain activation energy. Now, another requirements for the collision theory, yes, particles must collide and there must be sufficient energy. Another one is the correct orientation or the correct angle that they must hit. No? So I'll go back to my simulation here. And let us say, yes, I will provide what's happening? Um, I will provide enough. Can I adjust this? Try to reload our launcher and see if we can manipulate the angle here. Can we manipulate? Maybe we have to choose the angle shot. There you go. Now let us say let's manipulate the angle maybe in that, and then the energy that we will exert will still exceed, no, the total energy needed, but we'll just change the angle a bit. And yes, it hits there is a collision, then there is, I think, sufficient energy. But what happens is that in the whitish or the grayish line here is not even passing the transition state point, which means that there is no chemical reaction happening here, because here the whitish or grayish vertical line does not pass through or didn't pass through the transition state point. So in other words, the angle of collision was not correct. The orientation of collision was not correct. So why is the orientation or angle of collision important for a chemical reaction to happen? Now, let's take a look at an example here of, if you can still remember in the previous lecture that I have, I discussed about an ion-dipole interaction, right? Now, let us say you have here a polar compound or a dipole, and then you have here sodium. Now, definitely, we can say that this polar molecule, since this is a partially negative charge here, it's partially positive charge in this area, then we can say that if there's a sodium ion here, which is positively charged, it will attract, no, because this is negative. But what if we will hit and we will make sodium ion collide with the partially positive side of this polar molecule? Now, definitely there will be no interaction. There will be an interaction, but they will not be what? They will not be able to combine, because obviously they are both positively charged. The same thing with, you have here an iodine ion. So it's negatively charged. It attracts with this positively charged, slightly positive charge part of a polar molecule, because they are opposite charges. But what if I will allow this to hit and collide with the other slightly negative charge of this molecule? Then the two will repel. So in short, correct orientation of the collision must be taken into account for a chemical reaction to happen. So number one, there must be collision, and in the collision, there must be sufficient energy, but the sufficient energy is not enough for a chemical reaction to happen. The correct orientation must also be observed. So in other words, chemical reactions do not easily happen, but they do require different conditions. And I think that's very important, that your chemical reaction just do not happen that instantly or that easily, because if chemical reactions just happen easily, then your fruit will just ripen so fast. Your iron appliances will just easily get rusted. Your meat will easily get spoiled. Your our body will easily get aged, no? So there are important factors that must be fulfilled for a chemical reaction to happen. Let's take a look at the other factors that affect the rate of reactions, no? Temperature is an example of this. No, um, I think the bottom line here is that if you have a higher temperature, you will have a faster chemical reaction. There will be a faster rate of reaction. So if I go back to my simulation here, now what happens if I will increase the temperature of my system? No, say for instance, I have here particle A. All right, I have here different particles. Okay, I have 13 particles there. And let us try to raise the temperature and observe what will be their behavior when we continuously increase temperature. So as you may observe, the collisions become faster and faster. And since the collisions become faster and faster, we say that the rate of reaction also will become faster. So that's how temperature affects the rate of reaction. The higher temperature, the faster uh, the faster reaction you will get in your substances. So this is why we have the concept of refrigeration. Say if it's Christmas season, if you buy fruits and vegetables, diba, usually you buy so much or so many fruits and vegetables during the season. Then of course you cannot consume all of this in the Christmas Eve or in the New Year's Eve. So you have to put these fruits inside a refrigerator to lower the temperature so that they will not uh, get spoiled faster or easier or easily rather, no, or even with other products, let's say your milk or even your medicine or some of your leftover food, you put them inside the refrigerator because by lowering the temperature, we also speed down the rate of reactions of the substances present, no, in our food, fruits, and vegetables. Aside from temperature, there is another factor that you need to consider, and that is the concentration of your reactants. No, so basically, the core concept here is that the more concentration or the higher concentration you have, the faster rate of reaction you will also have among your substances or reactants. So, is in the diagram. Okay, if you compare here a low concentration of acid versus high concentration of acid, then the reaction of the acid and the marble will be faster, right? So if we go back to here in our um, simulation, no, let's say um, we have 9 particles there. Okay, and then we will add more particles from 9 to say uh, 50 now particles. You will observe that there will be a faster collision and therefore faster reaction in your system. I think this is the most common example that I can provide to you is, for example, you have here detergent powder. No, when you wash your clothes or your curtains or your rugs or your say bags or whatever you want to wash. No, say you have here 2 pitchers of detergent powders. Now, if we put this say in a pail of water, of course, an evidence of chemical reaction here is you will produce bubbles. No, so if you compare setup A and setup B, which of the following setups will produce more bubbles? So definitely it's setup A because setup A have more concentration or have more detergent powders. So that's the message of the concentration here. So the more particles per unit volume, then the rate of reaction increases. So that is the temperature, the concentration, and the next one is the surface area. No? So the surface area, the same with temperature and the um, concentration, the surface area also is the same. So the more surface area is exposed, no, to interactions, then there will be more collisions, and therefore there will be faster reaction. More surface area exposed, more collisions, and there will be a faster reaction. So in the representation here, if you have solid pieces here of your substance and then you allow it to react with other particles, there is limited reaction that's happening, no? Compared to ones that is crushed or subdivided into pieces. Another common example I can provide to you is if you compare the reaction rate of a detergent bar versus a detergent powder. So obviously, your detergent bar, if you measure the surface area of this, no, the exposure to the surface area per particle, this is limited compared to the subdivided surface area exposed, no, by these pieces of substances here or particles compared to a detergent powder. So between set A and set B, we expect that set B will react faster compared to set A. So that's how surface area affects the rate of reaction among and between your substances. So in summary, there are different conditions for your reactions to happen. The particles must collide, there must be sufficient energy, and there must be correct orientation or angle of collision. More importantly, you also need to consider the temperature, the concentration, and the surface area. Up next, that we'll be talking about here is going to be catalyst and the collision theory still, how this affect our rate of reaction. That will be our next lecture. Thank you very much, and I hope you learned something from this discussion.